Right. Welcome everyone to this Monash Cybersecurity Seminar. Today we are happy to welcome Yilei Chen from Tsinghua University, and he is an assistant professor there. Before joining Tsinghua University, he was a researcher at Visa Research, and in 2018 he got his PhD from Boston University under the supervision of Professor Ron Canetti and Professor Leonid Reizin. And Yilei's research interest is in the cryptography, especially in the areas of lattice-based and quantum computation. And today he will talk to us about Fiat-Shamir transformation, and we will answer whether it requires a cryptographic hash function. Thank you very much, Yilei. The scene is yours.
All right, thank you. Thank you, Mohammed, for your warm introduction, and thanks everyone for joining my talk. Let me share my screen first. All right, hopefully it works.
Yeah, thank you.
Okay, great. This talk will be about a question. So the title is a question: does Fiat-Shamir transformation require a cryptographic hash function? So another brief introduction of myself. I just recently joined Tsinghua University, and I more or less work on cryptography with a focus on lattice-based crypto and quantum, and also Fiat-Shamir is also a topic that I work a lot about. And I'm happy to join virtually for the Monash University seminar. And I just Googled it seems like a Monash University travel globally again, and I'm happy to visit the real campus. But today, let me just take the chance of the online talk to use one of my recent research work on the Fiat-Shamir heuristic. And this is a joint work with Alex Lombardi from MIMA and Willy Gua. All of them have been to Boston, in fact, but although the work is not done in Boston. So, okay, so let me start by introducing the topic, and by the way, so the talk will be so this talk will be touching a relatively elementary topic into cryptography. So if you have any questions or any thoughts during the talk, please feel free to interrupt me, and also you can type your question in the chat, and the talk can be structured in any length, so don't worry about the timing. Okay, so let me begin by tell you a little bit about the problem of Fiat-Shamir heuristic. So let me see how to click. Okay, so first, what is the Fiat-Shamir transformation? Give me a moment. Let me restructure my screen. Otherwise, I can see it. All right. Wait a moment. Okay. So what is the Fiat-Shamir transformation? So to talk about Fiat-Shamir transformation, let me first tell you about what is interactive proof, although most of the audience should know it. So in an interactive proof, what we think about, there's a prover and the verifier. The prover typically wants to convince the verifier about some statement. For example, either the statement is in some language. For example, you want to convince the verifier that an instance is a clause is satisfiable, or the prover wants to convince the verifier that she knows the secret of some random instance X. So typically it's for these two kinds of purpose. And usually for interactive proof, we require it to satisfy completeness, meaning that if the statement is true, the prover should be able to convince the verifier with high probability. And we also require the interactive proof to satisfy soundness, meaning if the statement is false, then the prover should only win with negligible probability. And a little bit about the terminology here, just in case you are not familiar with this kind of terminology. So when we say an interactive proof is a proof, it means the soundness holds for computationally unbounded prover. The typical examples are the traditional zero knowledge proof of Hamiltonicity given by Bloom, and also the three-round proof for zero, not three-rounded, but the proof of the zero knowledge proof for three coloring given by GMW. Another case of interactive proof, we call them argument, meaning that the soundness only holds where the prover is computationally bounded. So the typical example is Schnorr's interactive protocol for proving the knowledge of some exponent. So in this talk, whether the protocol is a proof or an argument will make a kind of a big difference. So that's why I emphasize here. I will also emphasize later. So after introducing what is an interactive proof, let me tell you what is the Fiat-Shamir heuristic. So Fiat-Shamir heuristic is a very popular way and a very efficient way of constructing efficient non-interactive protocol from an interactive protocol. So think about you have a multiple round interactive protocol where what the verifier is doing is just to toss a random coin. The typical scenario of the protocol is that the prover gives some commitment, and the verifier will give a challenge, and the prover is supposed to be able to answer or open the commitment according to the challenge, or it answers the challenge the other way around. So typically we call it random coin C because it's typically a challenge. But the whole point is it's just a purely random string chosen by the verifier. So if the three-round protocol looks like this, then we call it a public coin three-round protocol or multiple round protocol. So the idea of Fiat-Shamir is the following. So if you have a very, very good hash function, here very, very good means the hash function is purely cryptographic. And if you hash down any string, it will give you a random looking output. So this is the rough definition of very, very good hash function. So if you have such a very, very good hash function, then why don't you collapse the three-round protocol in the following way? You just first output the first message, and then apply the hash function on the first message to generate the second message. And then, since the hash function is very, very good, the second message C is supposed to look like random. So it's exactly simulating what you see in an interactive protocol. And therefore, you continue by answering the third message according to the first message and second message in exactly the same fashion in the interactive protocol. So this is the idea of Fiat-Shamir transformation. Namely, if you have a very good hash function, then you can transform any interactive public coin protocol into a non-interactive one or a signature. So in this case, let me give you an example, which is going to be Schnorr's ID protocol and applying Fiat-Shamir to Schnorr's signature. So this is an example which is kind of well known, but since I'm going to talk about our new observation of this protocol, let me kind of reintroduce this protocol, or introduce this protocol for the new students who join. So let's see how Fiat-Shamir work on Schnorr's three-round protocol. So what is Schnorr's three-round protocol? You can think about Schnorr's three-round protocol as the prover trying to prove that I know a secret S, and the secret is in the exponent of some discrete log instance. And I want to prove that, I want to convince the verifier that I know the secret without revealing what is S. So here is what the prover do. So the prover will sample a random string R and kind of output a capital R due to the lowercase r. So this is sort of a commitment to a secret randomness, you can think in that way. And the verifier will toss a random challenge C, and in the end, the prover will output Z equals to R plus CS Here I ignore all the the size of the group. So think about the group has size P, and this is done like as a group operation. C is as large as the group size, and the Z is done by R plus CS mod P. So intuitively, these three messages, they don't review S. And then let's see how the verifier verifies. The verifier will take all the public key S and all the transcriptions in the three-round protocol and compute R times S to the C, and check whether it equals to G to the Z. And let's see why the correctness holds. We open G to the Z, it goes to G to the R plus CS, and therefore G to the R goes to the first of R, and G to the CS goes to capital S to the C. Okay, so if the prover do know the secret S, then obviously it's able to come up with all the strings. And you can also prove that if the prover does not know S, then coming up with some strings that let the verifier accept is as hard as solving the discrete log problem. Okay, so let's see how to convert this one to a signature scheme by applying Fiat-Shamir. So, and also to make a signature scheme, we also need to take care about how to put the message here. So the way we take a message is to put it into the domain of the hash function and let the hash function be applied on the first message R and also the message to be signed M, and come up with the challenge C. So the signature will look like first outputting R equals to G to the R for some lowercase r, and then output C equals to H of R and M, and then output Z as the response of R and C, just look like the original three-round protocol. And what the verifier do is check as it is in the Schnorr signature, and in addition, it also checks whether H of R and M equals to C. So this completes the description of Schnorr's signature. It's exactly applying Fiat-Shamir over Schnorr's three-round protocol, and about the hash function is as good as a random function. Even if you see the key, then this is a very good signature. And by the way, this is a very popular signature used in practice. Sorry, I cannot. All right. So let me continue. So this gives an example of the application of Fiat-Shamir on some protocol. So what do we know about the security of Fiat-Shamir in general? So, initially, Fiat-Shamir just proposed this idea as a heuristic way of constructing efficient signature schemes, and also obviously non-interactive zero knowledge. But it took a while for them for other people to formalize and to prove in which sense this idea is secure. In other words, what do we need to assume for the hash function to make this idea sound, right? And in 1996, Preimage and Stern, they proved that if you model H as a random oracle, then this idea is secure. And in fact, this idea means for Fiat-Shamir applying on any interactive protocol, the resulting protocol is secure. And although I didn't write on the slides, recently there have been some work on showing that if you apply this idea, if you model H as a quantum random oracle model, meaning that if the three-round protocol has some quantum knowledge, then the resulting protocol is also sound under some circumstance of the original three-round protocol. So this assumes that we really model H as a random oracle. So this is, by the way, still a very efficient way of constructing signature, and there are no, let's say, real counterexample. But in theory, there is a counterexample that I will describe in a second. So what is really intriguing is that in 2003, Goldwasser and Yilei, they show that there exists a three-round argument system such that FiatShamir is insecure with any concrete hash function, meaning that if you don't model the hash function as a random oracle, meaning that you can see the key and you can use the key, the attacker will make explicit use of the key in violating the soundness of the protocol. So in this sense, they show that there exists an intriggering three-round argument scheme, such that no matter how your hash function look like, the resulting Fiat-Shamir transformation is going to be insecure for any concrete hash functions. So this really gives a very intriguing question to the area of Fiat-Shamir. So it gives you a counterexample in some sense to random oracle, and this, it raised the question of whether this really using Fiat-Shamir really gives a threat to the crypto system used today. And so still after many years, it's still a popular way of constructing practical snarks, meaning that succinct non-interactive arguments, NISIC and digital signatures. But it's hard to argue security in the standard model, where standard model means that argue security without random oracles. So it's only over the past 4 years that we have positive results for analyzing Fiat-Shamir for concrete cryptographic assumptions, meaning that we don't use random oracle. So this means that we can give a concrete property for the hash function and say we can build a hash function with such property from some kind of assumptions, they are falsifiable, and also such a property of hash function is sufficient for imply Fiat-Shamir for some protocol. So obviously it's not going to capture the impossibility of Goldwasser and Yilei because that's an unconditional impossibility result, but it will capture a large class of protocols that is not including the counterexample. And let me tell you a little bit. So all of these positive results, they go through a property of hash function called correlation intractability. And these works, they all build correlation intractable hash functions from various look of all these kind of results. And the common feature of these results is that they all work for proofs, meaning that it only works for applying Fiat-Shamir on a public key three-round protocol, whereas the soundness holds for computationally unbounded prover. And over the past 4 years, the assumptions get weakened, and for specific kind of proofs, the assumption can be as standard as standard LWE. Still, we don't know how to build it from one-way function, but doing it from many with errors is still a very convincing argument. And there are more work which that I even didn't include in the slides. Like using this technique, you can also construct a lot of non-interactive protocols just using standard assumption without using random model. So let me emphasize here that what is the open problem at the time. So still, it's a largely open, widely open problem of understanding how to do Fiat-Shamir for arguments without using random oracle, and also how to do Fiat-Shamir for what kind of argument that is able to avoid the Goldwasser-Yilei impossibility results. And in fact, if you think about all the application of Fiat-Shamir, the real interesting applications are really these ones that are arguments. For example, the Schneiders three-round protocol and its generalization of Vadims and many post-quantum signature schemes, and also snarks for MP from applying Fiat-Shamir over Yilei. So really, this example, we don't know any positive results for them. So these are the open problems well, I think they are also still open problems right now, even after my talk today. And I think it's fair to say that is to understand how to analyze Fiat-Shamir for arguments without going through random oracle. So before I continue, any questions about what I have said so far? Okay. So if not, or maybe you are thinking, then let me continue. You can still ask them in the chat. So in this work, we also think about more fundamental questions. Previously, we say, if the hash function is good enough or it's cryptographic enough, then it's supposed to be, at least one way or very contrived, so that the challenge, it looks like a random string, and that's why the Fiat-Shamir heuristic makes sense. And a similar question is also asked in the original paper of Blair and Rogway when they defined the random oracle model. So think about the hash function h as, it should be very complex, and it shouldn't reveal any structure in order for the Fiat-Shamir heuristic to work, or in general for the random oracle methodology to work. And if we think about what's the necessary complexity of a hash function which is sufficient for Fiat-Shamir, in some sense we have never seriously think about this question, and this is one of our motivation of think about how easy can a Fiat-Shamir hash function could be, even without trying to target in the open problems. I think this is also a meaningful question. So in the rest of the talk, I'm gonna tell you our new result with Alex from me and Willie about some of our small observation on applying Fiat-Shamir on some specific protocol. And the surprising part of the result is saying that if you want to work on Fiat-Shamir for Schnorr or Lubashevsky's protocol, it actually does not require cryptographic hash function. And to tell you about that, let me first recall the three-round argument system by Schnorr and Lubashevsky's, and let me intuitive difficulty of proving Fiat-Shamir from standard harness assumptions. Then let me tell you about our positive results. And in the end, I will conclude with open problems. Okay, so let me record the Schnorr's protocol again. And we have seen that Schnorr's protocol has the structure of R, C, and Z. And right now, let me tell you about the difficulty of analyzing Fiat-Shamir. And to make our life simpler, let's think about Fiat-Shamir for Schnorr's signature without a message. And in some sense, proving the soundness without thinking about the message is already contrived enough. It will give us, what's the barrier of tackling this problem. Okay, so what is the difficulty of proving security of Schnorr signature, in this context? So to explain the intuitive difficulty, let me highlight all the unknowns to be filled in the equations in the red color. So in a sense, all what we need to do is say, for the signature scheme, we want to prove that given G and G to the S equals to capital S, it's hard to come up with RZ such that R times S to the h of R, which is the hash of R, which is originally C, but you can replace the variable by h of R, and prove that R times this value equals to GZ. So I reduce three unknowns to two. Right now, your task is to come up with R and Z such that this equation holds. And so let's think about what do we want to prove. We want to say, come up with R and Z to satisfy this equation is hard for some fixed hash function. And we also recall that the discrete log assumption says, given G and Y, come up with X is difficult. So if we want to prove the security of Schnorr signature based on, for example, discrete log assumption, you will face the problem that the actual unknown in this equation, they appear kind of in arbitrary places. Some of them appear in the exponent, and some of them appear in the in the group. In fact, it's a ring if you define it in this way. And it's not a ring, but it's like someone appears in the as a group element, some appears in the exponent. So the unknowns are all over the place. It's not like the traditional discrete log problem. It's not as clear as that. So this is kind of the intuitive difficulty of basing any Fiat-Shamir task on standard assumption, is that they typically mess up all the unknowns into the place of the domain and the range of your favorite one-way function, and it makes things complex. So let me also move to Vadim's signature, and you will see a similar problem there. So Vadim's signature is it's a variant of Schnorr signature. So to introduce Vadim's signature scheme, let me also tell you a little bit about the short integer solution problem. So it's a typical lattice problem that says, give you a random matrix A and a random target T, find a short preimage is hard. So this is the assumption of the short integer solution problem. You can think about the task as find a short linear combination of A. So the whole point is we require the vector to be short. This makes the problem difficult. Okay, so let's see how to make use of the SIS problem to make a three-round protocol. So Vadim's protocol is an exact analog of Schnorr's protocol, except that the hard problem is replaced by SIS. The hard problem is no longer the discrete log. So in Vadim's protocol, you're trying to prove that a short matrix X such that Y equals to AX. The public key is going to be A and Y. Everything is mod P, by the way. So to prove such a statement, the prover sample a short vector R and output R equals to A times lowercase r. And the verifier will toss a short random vector C. Here it's required to be short because you need to combine it with the SIS problem. And in the end, the prover output R equals to Z equals to R plus XC. It's exactly like R plus CS in the Schnorr's protocol. And in the end, the verifier put back a Z and R and C in the original way as Schnorr's protocol. It's just replaced by the corresponding SIS instance. It looks like AZ equals to R plus YC. And if you open the right-hand side, you will see R plus YC equals to A parenthesis with R plus XC. And this is exactly Z. And in addition, you also check whether Z is short or not. And this completes the description of Vadim's protocol. And to do Fiat-Shamir, it's the same idea. You apply a hash function on R and output to short vector C. And in the end, you also check together. So let me now tell you, what's the intuitive difficulty of proving the soundness of Fiat-Shamir for Vadim's protocol. It's actually exactly the same feature as what we see in Schnorr's protocol, namely that if you rewrite all the variables into 2, you will see that the problem is you are supposed to come up with Z and R such that it satisfies an equation, and the unknowns are all over the place. It appears in the domain of the I times one-way function, right? So Z is supposed to be a short solution, and R is actually appear in the range. Recall that in the SIS problem, you're supposed to be find a short X given a fixed T, but now you have some freedom of choosing the it's all over the place. It's not clear what's going on, and sort of it has a similar feature than Schnorr's protocol. So put them together. So these are the common forms of analyzing the Fiat-Shamir heuristic for Schnorr's protocol and Vadim's protocol. And actually, you will see this appears in all the other example you can think about when using Fiat-Shamir, is that the unknowns are all over the place, and it's not clear how to let the domain and the range of edge match the protocol, where match means, sort of you hope all the unknowns are in the domain of a one-way function, but they don't. Okay. So are there any questions about this explanation of the intuitive difficulty? Okay, so if not, let me continue. So the reason I introduced Vadim's protocol is that, in fact, we will first show a positive result for doing Fiat-Shamir for Vadim's protocol. In fact, this will be a more convincing answer than our solution for Schnorr's protocol. Okay, so let me continue. So to solve the Fiat-Shamir problem for Vadim's protocol, the observation is the following. So we observe that the unknowns R and Z, some of them appear in the, so Z appears in the domain of of the the SIS instance, and R appears in the range of the I-type one-way function, right? And in some sense, the hash function is mapping in the reverse direction, that it maps a long string to a short one. So in some sense, the hash function is the reverse of the I-type one-way function. So this reminds us that, okay, so this is a slide showing what I'm trying to say. The C should belong to the domain of the SIS function, and R should belong to the range of the SIS function. And the H is doing kind of in the reverse way. So this gives us a hint that why don't we use the H as the inverse of the SIS function? And here we use an observation that, or let's say a technique in lattice-based cryptography, say, why don't we use let H to be the famous bit decomposition function? Okay, so this is sort of one of the most important slides here. So let me say again, so in short, we observe that in Vadim's protocol, all the hash function, what the hash function doing is, or not say all, but the hash function is mapping an element which is supposed to be in the range of SIS to an element which is supposed to be in the domain of SIS. So it's showing that my network is unstable, but if you want me to reconnect or re-speak something, please let me know. Okay, otherwise I will continue. So
yeah, I think that's okay. We heard, I think the slides were delayed a bit, but we heard most of it.
Oh, I see. Okay. So so by this observation, we hope to let S to be the reverse of the SI function, where one of the choices to let S to be H to the bit decomposition function. Okay, so let me tell you what it is. So previously I said I-type one-way function, it holds, I mean the one-wayness holds when A is a random matrix. I mean, we believe it's hard when A is a random matrix. But in fact, SIS is easy if the public matrix has some special structure. For example, if the public matrix, it looks like the following. So almost everywhere of the public matrix is 0, except the first few entry of the first line is like 1, 2, 4, 8, up to 2 to the k minus 1. And the second line starts from the case value is 1, 2, 4, 8 again. And in such a shape, then solving SIS of this matrix is actually simple, because we can just take the bit composition of T as the solution, as the short solution of such a as such a solution. So for example, if your T is 6, you take the bit decomposition of 6 as 110, and if you put 110 here, you obviously see that this times this equals to T mod Q. So this is an obviously efficiently computable function, namely bit decomposition. In the next, we will show you how to use the bit decomposition as a hash function. So our hash function for applying Vadims signature scheme is exactly the G inverse function, which we call the bit decomposition. Here, G represents this matrix, the blue matrix, and the G inverse is inverse function. Okay, so let us try to see what happens if we put the G inverse function into the Fiat-Shamir transformation. So if we say G inverse of R equals to C, this means G times C equals to R, where G is the the power of 2 matrix, 1, 2, 4, 8 matrix. So therefore, we can rewrite the equations with the unknown in the following way. We can write R as G times C, and G inverse of R becomes C, and therefore you can rearrange all the unknowns to the right-hand side of the multiplication of the matrix vector multiplication. And this time all the unknowns are becoming short because of the rearrange of the variables. And because G and G inverse, they are bijective, so you can write the exact inverse in the exact form. And then you can further rearrange to make put the C together. And now the question becomes: given A and G plus Y, find Z and C, which are short, and AZ equals to G plus Y times C. And by a further rearrange, you can see this is exactly solving the SIS instance where the public matrix is A concatenate with G plus Y. Okay, so since A is a random matrix and Y is close to random by the leftover hash lemma, you can prove A concatenate with G plus Y is statistically close to random, and this becomes a valid SIS instance. So therefore, this is our main theorem that if we take G inverse as the hash function for Vadims signature, then breaking the soundness means you can find Z and R, means you can find G and C, such that Z and C, if you put them together, they becomes a short integer solution to A and G plus Y. Okay, so
can I ask a question here, Yilei?
Yeah, please.
So don't we need here the fact that Y is honestly generated?
Right. Here we need the fact that Y is honestly generated.
Okay. And okay.
Yeah. So because in Schnorr's protocol, in Vadims protocol, if you suppose Y is equal to A times X, where X has sufficient entropy, then in this case, Y is statistically close to random. If this is true, then you have the feature that Y is random. I guess that's what your question, right?
Yeah, but what if Y is not of that form? I mean, because I don't think, do we have a proof that Y is of that form?
It's not clear, right? So if Y is maliciously generated, then the prover might know a trapdoor of Y. In that case, it might be able to, break the soundness, right?
Mm-hmm.
So in some sense, it will be interesting in the scenario where the prover, so in some sense that when the instance is not generated by the prover, this will be interesting. Right.
Okay.
Okay. So you will say, okay, fine. So what's the implication of this construction of using, G inverse as the hash function. So the implication could be, do we get a new signature scheme by doing this way, or do we? Obviously we have the implications that the hash function can be look like almost trivial, right? It's just doing bit decomposition. It's obviously not a one-way function, but let's put that later. Let's see the signature scheme from here. So it turns out this is not the case. And so in the bottom of the slides, I say, in fact, although this is not kind of like, this is not our motivation, but this is actually an accidental rediscovery of the lattice trapdoor signature scheme designed by Michantra and Pikert. So recall in the work of Michantra and Pikert, they design a lattice signature scheme by constructing a SIS instance with a trapdoor. And the trapdoor exactly looks like A concatenate with a G matrix plus some A times small x. So in fact, break soundness, we show that break the soundness it's equal to solving the SIs for this. And over the signature scheme of MP12, it also have the feature that the owner of the secret key X is able to sort of generating is sort of the owner of the trapdoor. Therefore, it's able to sample a short preimage using the trapdoor. And here we're kind of rediscovering the structure of the trapdoor designed by Michantra and Pikert. So rather than giving a new signature scheme, we only show a connection between Vadim's signature and the signature of MP12. But in some sense, this is also a surprising connection because this connection was never publicly mentioned before. And it's somewhat surprising to see that the trapdoor of MP12 can be seen in another way from Fiat-Shamir transformation. And here I would also like to say, in fact, using G inverse at many places is sort of the core of lattice-based cryptography. In fact, in a slide of Chris Pikert of lattice to cryptography, he pointed out that by putting G in different places, you get different features of all the fancy techniques of lattice-based cryptography. For example, if you put the G in the public key, you get the trapdoor function, like what I said. And if you put the G in the evaluation key of BV11, if you put G in the ciphertext, you get the FHE of GSW13. And today we show that if you put the G, or rather G inverse as the hash function, then you can rediscover the lattice trapdoor by taking the Fiat-Shamir, which is somewhat expected after you see all the fancy applications of the G matrix. So okay, so this is a rediscovery, but are there more implications of this construction, namely taking G inverse as the hash function? So here's a more like a philosophical implication. It says that Fiat-Shamir hash function can be non-cryptographic. If you stare at the function G inverse, namely take the bit decomposition of some value, it's really hard to imagine there's anything cryptographic there, namely there's any hardness embedding in this hash function. But to make a formal analysis of what does it mean by cryptographic, we first need to define what does it mean by for a hash function to be cryptographic or non-cryptographic. So the first treatment is, if a cryptographer thinks something is non-cryptographic, then something is non-cryptographic. Namely, it is what it is. Of course, we are more serious, and we explicitly define a security property we explicitly give a definition for a function to be non-cryptographic, And this definition is more involved. And on a high level, it has to involve that the security involving this hash function has to have a gap between statistical and computational attackers. And some more care has to be done in making this cryptographic notion to give it some more context. But roughly, you need to define again which has a gap between the statistical and the computational attacker. Okay, but in this talk, I will go for the first definition that we just assume that when we see a hash function, we all agree it's non-cryptographic, and then we are happy. Okay, so I think I have another like 15 minutes or 10 minutes. So let me tell you a little bit about how we use this idea that we can use a non-cryptographic hash function into Schneiders protocol, which more people are familiar about. So driven by our observation, in some sense, the H function is just the inverse of the discrete log problem. But unfortunately, in the discrete log world, there's no tools like a bit decomposition. So in some sense, we don't have a very satisfactory answer for the same question in discrete log. But we have a different type of answer, is that how about we just let the hash function to take the randomness in the first message and the message, and we just sum them up mod p, and assuming we only work with short message and we think about the p as the group size. So how about we do this? And right now the task is that you need to find r, n, m, and z such that r times s to the r plus m, whatever this means, equals to g to the z, and we assume the m is in a small subspace over 0 to p minus 1. Otherwise, you can obviously break this protocol. Okay, so in fact, we prove that if you use this plus as the discrete log, the Schneiders hash function, then still finding R and M and Z is hard in the generic group model. So let me skip this line. And okay, so if you can prove that the idea of R plus M is a good idea in a generic group model, it seems to have a very strange implication, meaning that a very popular signature scheme can be instantiated with almost a trivial hash function. It's just sum up with the randomness and end the message, assuming the message is in a small subspace of the group size. Okay, so after our paper initially appeared on ePrint, which is almost a year ago, which is more than a year ago, it interests some researchers, and some of them ask, this looks really weird, but because it yields significant improvement for Schneiders signature circuits. It's really simple, and can we use this right away? Of course. Some crypto big shots just to say, no, please don't conclude anything like this at this moment. That theorem only holds in the generic group model is theoretically very interesting, but I want to use it currently in this shape, and there are more discussion. So I don't use Twitter, so I don't really know what's going on afterwards. But anyway, obviously, if this really works, then it's somewhat surprising. So as serious cryptographers, we are not really satisfied by in a solution which is only secure in the generic group model. We put it back into concrete group instantiations like the multiplicative group of finite field, and we really tackle this question to see whether this is a hard problem in any concrete group. It turns out that we find an attack, and it's really simple. So think about if you set R equals to -1 in the finite field discrete log, and you've set M to be 1 and the Z to be the discrete log of -1, So by a standard exercise, a discrete log of -1 is easy to solve. And then you put it in the exponent, you will see that the left-hand side is -1 times s, meaning it's -1, and then the right-hand side is due to the discrete log of -1 is -1, and it satisfies the equation. You don't even need to know the secret s. You can come up with such r and m and z, and they look very natural. So this attack actually used the non-generic part in the finite field, meaning that, in fact, all our familiar group representation like field or elliptic curve, they have more or less non-generic parts. And this attack actually explicitly used the non-generic part, meaning that the discrete log of -1 is easy to compute, and the -1 is a special symbol in the finite field discrete log problem. And you can find a similar attack if you use the elliptic curve representation, and I think I have written it in the paper. So, but this type of attack can be captured by the generic group model with preprocessing, and in fact, we propose another fix by including a key in the hash function, and the key is just a random string of size p, and the hash function is going to be r plus m plus k, and for this one we are able to prove it's secure in the preprocessing generic group model, and we also don't find any other attack for this construction. Any questions about this part? I think I'm gonna close to the end of the description of Schnorr signature.
I might ask a question. Actually, I was going to ask, so since S is the public key, I was going to say, like, can we put S inside the hash, which basically just corresponds to replacing this K with S? Does that help, or?
Oh, I see. So your suggestion is put the capital S into the hash function.
Yeah, so it will compute R plus M plus S, not P.
I think that also works. So you assume S is something that you can put into the hash function. I see. But this has this might have a problem that I don't know. This might have a problem, but I'm not able to come up with a counterexample now. So the key is to say, if you put S in the place of K, then you might be able to choose R as reverse of S. Suppose it's a group element. If you don't put the size big enough, it might be. And then put M into S. So, the key is to make R plus M plus S equals to 0. And then come up with the rest to cancel them out. It might work, I'm not sure. But
okay. Yeah, I was just thinking whether you already thought about this.
Right. So there are different variants, and they may all be provable in the generic group model, but somehow the non-generic part in the concrete group is really annoying for this for this specific application of generic group. So I would say it's hard to say, and we need to take a closer look to see whether another suggestion work or not.
Okay. Yeah. Thank you.
Okay, so I guess my time is closing to the end, so let me go to the summary. So, okay, so discussions and open problems. So previously I have given you 2 examples where, to instantiate the Fiat-Shamir hash function, you almost require a non-cryptographic hash function. So in the paper, we also discuss what kind of protocol does require a cryptographic hash function, but it at least need a one-way function. It turns out there are protocols where cryptographic hash function is necessary, and the examples include the Brom's protocol and a small challenge version of Schnorr, and many other post-quantum signature scheme like the signature scheme from isogeny. They do at least require a cryptographic hardness. And still what is open is, I think, for proving Fiat-Shamir for a larger class of arguments I mean, the typical difficulty is that the hash function is going to mess up all the domain and the range of a typical one-way function you may like. So that's why it's difficult to analyze any of them. And it's still open for post-quantum signatures, many of them, and Snark for MP from Fiat-Shamir over Killian-Mikhaili. And in some sense, for Schnorr and Lubashevsky, if you want to make it more general, it's almost also open. We just give two special examples where the hash function might be trivial. So sort of this is the summary of my talk, and thanks for your time. I'm happy to take more questions.
Thank you very much, Yilei, for your very interesting talk. Any questions from the audience? You might raise your hand if you want to ask a question, or just speak up if you are in the panelists.
Hi, Yilei. Thanks for the talk. Yeah, I was wondering for this connection between Lubashevsky and Mityantia-Packard signature. So does it give a Mityantia-Packard signature that doesn't use Gaussian sampling but uses only, say, uniform rejection sampling? Because like in Lubashevsky, it's common to use uniform rather than Gaussian.
Right. So in fact, this is a great question, but this question has already been answered by a paper, I think 5 years or 4 years ago, by Daniel Wicks and Vadim. They have a paper saying that you can instantiate the MP12 signature with, for example, uniform preimage by exactly using rejection sampling. Over there, they just more explicitly describe how to rejection sampling that. It's not too difficult to see, in fact.
Okay. All right. Yeah. Thanks.
Vanessa, would you like to ask your question? You should be able to unmute yourself.
Thank you. I just wanted to ask, to come back to this question that Mohammed raised a little bit earlier. How much of a difference does it make whether the prover is allowed to choose the statement or not? So definitely in the early few examples you were talking about, we were only talking about a scenario in which the statement is given. Yeah, are there any results in which you can still prove things in this space even if the prover is trying to generate a problem statement of their choice?
I see. So that's a new question to me. I need to think about it. Just a brief thought suggests that I'm trying to make the question clear. You're saying maybe the prover is able to also generate the public key and convince the verifier that. But let me ask, in this case, let me try to see if I understand it correctly. So if Y is chosen by the prover, in this case, what's the interesting question?
Yeah, it's true, actually. Sorry, it was sort of a generic question about the Fiat-Shamir construction. You can think of other situations in which you would want to use the Fiat-Shamir construction for cases in which making it up might make sense. I agree, now that I've asked the question, it's not actually all that clear that it makes any sense in this case.
I think we have another. We do have another thought in a different context. It's saying it's phrased in the form of like Fiat-Shamir with adaptive soundness or whatever it means. It's more or less that it's kind of like after you see the hash function, you can choose the instance or you can choose the statement. Yes. In this case, do you have Fiat-Shamir transformation with adaptive soundness? For that kind of question, we do have a positive answer by using, I forgot the name, actually the FLS or the French-Lepoint-Shamir protocol. If you apply Fiat-Shamir over that protocol, then the first message is instance independent. And then if you apply Fiat-Shamir for that protocol, then it's automatically adaptive secure, but because, how to say that? Actually, I haven't come back to this question for a long time. I think if you can phrase the question into that format, meaning that in some case you can choose the instance after seeing the hash function, and then if you can plug in the this form of FAIS protocol, then I think the answer is it's doable. But in other cases, it's a tricky question. For example, here, if the public key is not, it's maliciously generated, then it's a tricky question. Depends on who generated it, I guess.
Cool. All right. Thank you. Thanks for a great talk.
Yeah. Thank you.
I think we have reached the end of the time. Thank you very much, everyone, for tuning in. And thank you, Yilei, again for your very interesting talk. Hope to see you all in the next seminar. See you, everyone. Bye.
Oh, yeah, thank you.